take a little sip of coffee while I wait for my streams to start. All right, looks like we are live. Good morning, everybody. I am really happy to be back. If you haven't been following me on Twitter, you might have been like, "Where's Rachel?" And I announced on YouTube that I've been really sick. I'm actually supposed to be in Indiana right now, but I was still running a fever on Monday, and I just couldn't travel. And I don't know if you can tell, my voice is. Hopefully my voice will be good for an hour today, and if it's not, we'll call it a little bit early. But I am really happy to be back. It's been too long, and get back into the reading club. So we've been reading about contextual word embeddings, which are, well, let me pause this so I'm not taxing my internet, which are word embeddings that are taken from language models. So they consider the sort of like whole sentence that the word was found in as a sequence with ordering and not just not just a bag of words. Sorry, that's what I was looking for. I might be a little bit spacey today, and forgive me if that's the case. Hello. Yes, I'm back. I'm happy to be back. And I will warn you right now, I'm probably going to have to cough at some point, and I can't mute the mic. That's what was asynchronizing the video and the audio, so they didn't match, which I at least find really painful to watch. So if I cough, I'll try to like duck over to the side and do it in my elbow, but it's not going to be great audio, and I'm sorry about that. So we had talked about looking at all of the different architectures that they were using to train these contextual word embeddings, which there were 3 different architectures they used. They used their bidirectional LSTMs, so that was the Elmo architecture that was proposed in the original paper. So this paper is by Peters et al., and the Elmo paper is by Peters et al., and it's the same Peters, it's the same research group. And they also did a gated convolutional neural network, and we talked a little bit about that 3 weeks ago. And then also self-attention, which is transformer models. And we've talked about transformers quite a lot on the channel. We've read quite a few transformer papers at this point. I think this is the fourth transformer paper, 3rd or 4th in there. So hello everybody, welcome. So we read about all of the different model architecture that they used for these contextual embeddings, and the sort of general trade-off seems to be that the LSTMs, the bidirectional LSTMs, the original Elmo architecture, has higher accuracy, but tends to be a little bit slower to train, which is just a quality of recurrent neural networks in general, because they're sequence-based, so you have to do the previous sequences before you do the following sequences, which is, or rather the previous part of the sequence before the following part of the sequence. Excuse me. Ooh, sorry. I'm going to try to stay hydrated so that the voice isn't too bad. But it's a little bit slower. So the transformers and the CNNs are faster, but tend to have, at least in this particular example, a little bit lower overall accuracy. It's sort of the trade-off that we've seen so far. And we were starting to look at, did we do this part? I'm trying to remember where we were. So we definitely read about the model types. We definitely talked about that trade-off. I'm trying to remember if we looked at the performance as word representations part. And I genuinely don't remember. Okay, we definitely haven't looked at this. In my defense, it has been a while, and also I've been very fevered, which is not the best for trying to remember a paper you read like 2 weeks ago. I'm actually gonna just check down here in another window real quick. What the last thing that we talked about was? I'm sorry, I warned you. I'm gonna try and keep that to a minimum, but I can only do so much. I just didn't want to miss 2 weeks in a row, and also, I'm getting cabin fever, y'all. I'm getting cabin fever real bad. YouTube. Oh, you might have noticed recently also, by the way, that youtube.com/Kaggle now takes you to Kaggle, and not just a random person who had that name for some reason. Reading group. Yes. And I wanted the... Why are they in this order? I don't know why the reading group playlist is in this order. I'm going to have to go back and recheck that. The second one, and we had gotten up to... okay, so we were looking at that page. Okay, so I think I talked about the tasks, but we didn't go over them in depth, if that sounds right to people who were here 2 weeks ago. So let's talk about evaluating these as word representations. In this section, we evaluate the quality of the pre-trained bidirectional language models as Elmo-like contextual word vectors in state-of-the-art models across a suite of 4 benchmark NLP tasks. And I definitely remember that we talked about all of these tasks, because I remember we looked at semantic role labeling for sure. For our model, Elmo representations. For this task, LSTM performed the best. Actually, I think we did read that. I should have checked this beforehand. I'm sorry. I was rushing to get this all together this morning because I didn't want to commit to doing this if I wasn't going to have a voice, and my voice is getting better, and I am drinking coffee, and I know I shouldn't drink coffee. But it is cold, and I never drink cold coffee, so that should help a little bit. Okay, well, basically, they do better than they seem to do equally well as other embedding models. Hello, everybody who's saying hello and welcome back. All right, yeah, no, I think this is where we ended up. Properties of contextual vectors. In this section, we examine the intrinsic properties of contextual vectors learned with BiLMs, bidirectional language models, focusing on those that are independent of the architecture details. Yeah, this is where we left off. Okay, I remember now. In particular, we seek to understand how familiar types of linguistic information, such as syntactic or co-referent relationships, are represented throughout the depth of the network. Our experiments show that deep BiLMs learn representations that vary with network depth, from morphology in the word embedding layer to local syntax in the lowest contextual layers, to semantic relationships such as co-reference in the upper layers. Okay, and this is what they promised in sort of the abstract, is that there's sort of a hierarchical grammatical information encoded in this contextual word embedding. We gain intuition and motivate our analysis, and this is a very strong claim, by the way, so I'm excited to see strong evidence. We gain intuition and motivate our analysis by first considering the inter-sentence contextual similarity of words and phrases. Then we show that, in contrast to traditional word vectors, the bidirectional language model BiLM word embeddings capture little semantic information that is instead represented in the contextual layers. Oh, capture little semantic information that is instead represented in the contextual layers. So they're saying that, so word vectors, like the sort of like core representational semantics sort of philosophy is that you shall know a word by a company it keeps, and if a word tends to show up near other words, then they probably have similar meanings. And the thing that they're saying here is because they're learning these contextual word embeddings that include information not only about what words are occurring together, but their position with regard to each other, that this is allowing them to sort of like, like titrate in chemistry, where you can like pull apart all of the different layers, but instead in a model, they're doing that with the different parts of grammar. So they're saying that their initial embedding doesn't actually have any semantic information and instead is having morphological information, and that the semantic information is in the contextual layer. Our analysis moves beyond single tokens by showing that a simple span representation based on the context vectors captures elements of phrasal syntax. Interesting. Okay, let's keep reading. Sorry, I'm just thinking about how this relates to cognition, because that's always the lens that I'm looking at. Like, I'm always looking at machine learning for language representation through the lens of what I know, of what we know, like as a species, about language representation cognitively and sort of in general. And I definitely think that words have meaning, and that for a human language user, not that there aren't human language users, for humans, words, or at least morphemes, are elements of that can have meaning in isolation, and this is suggesting that it's only in the context layers that we actually get some sort of semantic representation here. Interesting. Contextual similarity. Nearest neighbors using cosine similarity is a popular way to visualize the relationships encoded in word vectors, and we can apply a similar method to context vectors. As the BILMs use context vectors to pass information between layers in the network, this allows us to visualize how information is represented through the network. And context vectors. Okay, so they're just going to use the same sort of way that we use to look at similarity between word vectors for context vectors, and then I don't know how they're going to visualize it working throughout the network. So within sentence similarity. Figure 1 shows the intra-sentence contextual similarity between all pairs of words in a single sentence. Intra-sentence contextual similarity between all pairs of words in a single sentence using the 4-layer LSTM. Okay, so they've got all of the words in a single sentence, and then they're looking at all the possible pairs, and they're getting the contextual. And then from the LSTM, so using their context vector, they're looking at all of the pairs of words, and that's figure 1 here. From the figure, we make several observations. First, the lower layer, left, captures mostly local information, while the top layer, right, represents longer range relationships. Second, at the lowest layer, the BILM tends to place words from the same syntactic constituents in similar parts of the vector space. For example, the words in the noun phrase, the new International Space Station, are clustered together, similar to can, not, and the Russian government. All right, let's take a look. So we have a sentence here, and we're using the cosine similarity between words. Yeah. Taking the vectors from the first and then the fourth, so the bottom and then the top layer of this LSTM. The left panel, so this panel uses context vectors from the bottom. So this is the bottom layer, and this is the top layer. And they are suggesting that this layer is showing more constituency structure, and that this layer is showing more, what did they say it showed? Local information. Okay. So we do have high similarity between 2 and 2. Okay, so this is a repetition, so it would be, we'd expect it to have high similarity. I think that makes sense. But not the and the, interestingly, because here's the word the and here's the word the. To the, to maintain. So this is to maintain. To is part of the infinitive, to maintain. So that's in languages like French, you have like être is the infinitive of the sort of the verb to be. In English we have the word to in front of it. It's just the way that English is. It's also because Romance languages don't have that. That's why they say that you shouldn't split the infinitive, because you can't split the infinitive in Latin. And there was this weird historical thing where the scholarly tradition in English is really based on a scholarly tradition that was, monastic and clerical and draws heavily on Latin. And so Latin has this like weird status as a language that people really wanted to be like. Anyway. And there's some really weird stuff trying to prove that English is descended from Latin, which it is not. It is Germanic. Let me zoom in a little bit so we can look a little bit more closely at these figures. So here cannot has, so not and can have pretty close activation to each other. Oops, sorry, let me try and stay in frame a little bit better. The new and space station. So space station, no, sorry, international and space. So this has sort of, they're arguing that this has more local information, and that this is in some way being treated as a chunk. And then as we move up through the LSTM, so this is the first layer, up through the fourth layer, and the LSTM isn't gated. Well, I mean, all LSTMs are gated. Because they have a forget gate. As we move up to the top layer, they're arguing that we see more constituency structure. So the Russian government says it cannot afford to maintain Mir and meet obligations to the new International Space Station. So Mir has really low activation, presumably because it's it might be, well, it's not out of vocabulary because they trained on this, but it's probably a very infrequent word. Interestingly, the sentence end has very low activation. Interesting. So Mir and the seem to have the lowest cosine similarity, which is interesting because you don't usually use the with proper names. And this is the proper name. So maintain. Interesting. So afford to maintain here. It looks like to does not have a high cosine similarity to afford or maintain, but afford and maintain both have a pretty high cosine similarity to each other, and these are part of the same verb phrase. So that's interesting. And then also maintain, afford, and meet also have a fairly high cosine similarity to each other. Excuse me. And they are all says is a verb, afford, maintain, and meet. I think those are all, oh, sorry, can. Says, can, afford, maintain, and meet are all the verbs. Can is a little bit weird because it's a, there's a name for the type of verb that it is, and I do not remember what it is. It's an auxiliary, but it's something specifically. Ryan says, is this based on the similarity of the word embeddings? It's the similarity, cosine distance of the context embeddings as drawn from the first and the fourth layer of the bidirectional LSTM. So these are from the context embeddings. And I think the overall thing that you can see from these figures is that there is more activation. The cosine similarity between words is higher the closer they are to each other and highest to the word itself. We should hope it is. And that in the first layer and in the fourth layer, there's a higher cosine similarity between words that are farther apart. So says, it looks like, has a high cosine similarity to can, afford, maintain, and meet, which are the other verbs in the sentence. Afford has a high cosine similarity to says, afford, maintain, and meet. Again, the other verbs in the sentence. So that's very interesting. So it seems like it's not tagging part of speech. I don't want to say that, but it definitely has some strong patterns that correlate with part of speech. Yeah, lighter colored arrows. I think I read this. Sorry, I'm still a little bit out of it. Is how that I'm doing. And I don't know if you can tell, but my voice is really rough. Interesting. In addition, we can see how the BLM is implicitly learning other linguistic information in the upper layer. For example, all of the verbs says, can, afford, maintain, meet have high similarity, suggesting the BLM is capturing part of speech information. Oh, sorry, that's what I just said, and it's the next thing that they say in the paper. We can also see some hints that the model is implicitly learning to perform coreference resolution by considering the high contextual similarity of it to government, the head of its antecedent span. Section 5.3 provides empirical support for these observations. So government and it. Government, it. I guess it's kind of hard to tell because it's an area that's more lightly colored, so it's a little bit hard to see how strong that change is, but we can definitely see that it's stronger than it is here, for sure. So in the first layer, there's not a high contextual similarity, and in the fourth layer, there is. Well, it's higher. And now they're going to actually give us some empirical proof, which I'm excited to see. The observation that the BiLM's context vectors abruptly change its syntactic boundaries suggests we can also use them to form representations of spans or consecutive token sequences. To do so, given a span of S tokens from indices S0 to S1, we compute a span representation S0 to S1 I at layer I by concatenating the first and last context vectors with the element-wise product and difference of the first and last vectors. Ryan says, not much stronger than obligations, like 12 words away. Government, obligations. I think that's a little bit higher. It's hard to tell because it's in the background color of these is a little bit different. But yeah, I am interested to see this. So they're given a span of tokens, and they compute the span representation by concatenating, so just sort of like the first and last context vectors with the element-wise product and difference of the first and last vectors. And that's what this is saying. So they don't element-wise, so they don't do it for every vector. So they don't take the vector of every token in the span. They take the first and the last, and then they take the element-wise product, because they're vectors, and then difference, so subtraction, and then they, I see, so they concatenate it. So you have the first, the last, the product, and then the difference, and it's going to be one long strand. Sorry, so the output of this is a single vector. And I guess the reason that they do the first and the last is so that you can compare strands of an arbitrary length with a vector of the same length. Hop in the comments if that's not what you guys are getting from this math, but that's what I'm getting from this math, which could potentially be the wrong thing. Excuse me. I'm sorry. Figure 2 shows a T-SNE. Madden and Hinton 2008. I guess they're citing T-SNE. Visualization of span representations of 3,000 labeled chunks and 500 spans not labeled as chunks from Connell 2000 chunking dataset. Ryan says similarity is a bit weaker, but also it's so far away. Have to wonder how much of this is just noise and cherry picking an example that matches their belief. That is something that I had thought about. Yes. It's hard to say, but I think the sort of thing they're doing now is to show that this is something that is more broadly applicable. Okay, so they're looking at 3,000 labeled chunks. So I believe the Connell chunking data set is just sort of like asking people to demarcate where they think like, or is this a reasonable chunk of a sentence or not? And people tend to have pretty good intuitions about that. Oh, I'm sorry guys, being sick is the worst. And I wish I could mute, but that unsynchronizes the audio and video, and I think that that is worse than listening to someone sneeze, so I'm sorry. Okay, So I think they just like sort of like asked people to identify chunks. Thank you. Doi says, bless you. Okay, so they are clustering the representations, and then they are color coding them based on pre-labeled whether or not they're part of chunks or not. So this is from a hand-labeled data set. Section 5.3 evaluates whether we can use these span representations for constituency parsing. Okay, so they're so this is just showing a pattern, and then they're going to look at whether or not this this pattern is reliable enough to use in tasks. So let's zoom in a little bit. So this is a scooch it over a little bit. So the representation in space is based on the the distance measure that they're using, which is based on the first and the last items in the span. And then the color is based on hand labeling. And so what I'm noticing here is we do have some clusters. So it looks like adverb phrases, this ADVP, tend to be a little bit more scattered. Noun phrases tend to be pretty well clustered over here. Prepositional phrases tend to be pretty well clustered down here. S-bar, so that would be sentences. Are they using X-bar? Surely they're not using X-bar. X-bar is a really old theory that I don't think many people are using these days. So that would be like, Johnny said that I like apples would be an embedded sentence. So I believe that's what S-bar is the most tightly clustered. NP, which are noun phrases, are over here, and then verb phrases are in here, and that's, again, pretty tightly clustered. So there is definitely separation between these groups. They're not just random. What is random is these null phrases. I don't know if you can see, they're these little purple triangle shapes. Nope, the other way. There we go. Facing that way from your perspective. And they are sort of sprinkled over like poppy seeds. So here's one, here's some in here, here's some in here, here's some in here, here's some up here. They're really just sort of randomly sprinkled around. So I think what they're trying to show with this visualization is that random spans are not clustered. So that's the sort of the noise if you just take two random words, and that words that demarcate spans are actually in this space clustered together similarly, so that they're capturing something like, and it's not 100% accurate. You can see, especially I mentioned the adverb phrases are sort of like a little bit all over with the greatest density right in here. But I think what they're saying is that if this were just random, we'd see this pattern that we see with this sort of like purple sideways pointing triangle that are like poppy seeds on a bagel. They're all over. And then the rest of these are more like, I guess, mozzarella on a pizza. They're sort of like a pizza where like you tear the mozzarella chunks. So there's some like big chunks in the space that are associated with predetermined phrases, which is interesting. I find that actually pretty compelling. I think that's a good visualization of their point. As we can see, the spans are clustered by chunk type, confirming our intuition that the span representations capture elements of syntax. Oh right, we said that. Unsupervised pronominal coreference. We hypothesize, and they say see section 7 for visualizations of other models. Appendix for visualizations of other models. Unsupervised pronominal coreference. We hypothesize that the contextual similarity of coreferential mentions should be similar, as in many cases it is possible to replace them with their referent. So that's the idea. Like I can say, Billy took his ball and played football. I guess I was trying to think of a game that involves balls. So you could replace his with Billy's. You could say Billy ate a sandwich and he regretted it. You could say Billy ate a sandwich and Billy regretted it. So you can replace the co-referent chunk with the thing that it's co-referring to. That's what coreference means. If true, we should be able to use contextual similarity to perform unsupervised coreference resolution. There's some sort of coreference resolution thing going on Kaggle right now. That might be a helpful approach for y'all to take. To test this, we designed an experiment as follows. To allow trivially high mention similarities due to lexical overlap, we restricted to pronominal coreference resolutions. Sorry, that's exactly what the Kaggle competition is about. We took all sentences from the development set of the On2 Notes annotations in Connell 2012 shared task, Pradhan et al. 2012, that had a third-person pronoun, so his, hers, its, an antecedent in the same sentence, 904 sentences, and tested whether a system could identify the head word of the antecedent span given the pronoun location, so the first word of the span. So in the example, Jane and Billy ate pie and they liked it. I can, the head of that is probably going to be Jane. So Jane and Billy, they. So I'm going to define Jane as the first word in the span. In addition, by restricting to pronouns, systems are forced to rely on context to form their representation of the pronoun, as the surface form of the pronoun is uninformative. Well, it's like a little bit informative. As an upper bound on performance, the state-of-the-art coreference model from Lee et al. Excuse me. Okay, I'm not going to cough. Found an antecedent span with the head word 64% of the time. As a lower bound on performance, a simple baseline that chooses the closest noun occurring before the pronoun has an accuracy of 27%, and one that chooses the first noun in the sentence has an accuracy of 35%. Excuse me, I'm sorry. Sip of water. Ooh. If we add an additional rule to further restrict the antecedent nouns matching the pronoun in number, two antecedent nouns matching the pronoun in number, the accuracy is raised to 41 and 47% respectively. This I like. There's a clear, dumb baseline. They've tried really hard to make the baseline pretty good. They're comparing it to someone who did a good job on their system, and they're saying, where are we going to be? That's a nice experimental setup. 10 out of 10 would... Well, I guess 5 out of 5, because that's what it's either 5 point or 6 point is the ACL ranking scale. To use contextual representations to solve this task, we first compute the mean context vector of the smallest constituent with more than one word containing the pronoun, and subtract it from the pronoun's context vector. Oh, wow. Ooh, sorry. I guess I'm still tired. I've had a lot of naps this last week. This step is motivated by the above observation that local syntax is the dominant signal in the contextualized word vectors, and removing it improves the accuracies of our method. Okay, so they are finding the smallest constituent with more than one word containing the pronoun, and then subtract that from the pronoun's context vector. So this must be the context vector after the fourth level. So the one on the right in the figure, on the figure that we looked at above. Okay, so they're just they're removing local information because this is sort of like So if we were doing, so if we were looking at like we would look at this vector and then we would subtract this vector because this is telling us that says it can, or maybe says it cannot afford to maintain whatever. So it's sort of like local constituency structure is going to be more impactful than longer constituency structure, than the more distant constituency structure, which makes sense. Things that are closer tend to be more salient to humans in general. So I think that's pretty reasonable. If we're hoping that this is an approach that captures information about the system of language. Then we choose the noun with the highest contextual similarity. Okay, so they are doing some things. They are doing some labeling by hand here. So they are labeling the they need a label of the smallest constituent of more than one word containing the pronoun. So they need to know where the boundaries of that constituency structure are. So that's something that you need to have a priori information on to use this approach. And then they also need to know part of speech. So this would require constituency parsing and also part of speech parsing. Sorry, I'm trying to get into frame. So it would require constituency parsing and part of speech labeling, in addition to training context vectors. I'm just thinking. So this is a context vector trained on this particular sentence, but I thought that they were arguing that the context vectors could be transferred easily between sentences. So I guess you're going to have to retrain your vectors for your particular context. I'm trying to remember if we read about this before, and it's very possibly that we did, and I just am forgetting about it because I'm, again, not 100%. I'm like 87%. Then we choose the noun with the highest contextual similarity to the adjusted context vector that occurs before the pronoun and matches it in number. Okay, so that would be like singular versus plural. Yes, because we only have a singular plural distinction in English. Sorry. For a second I was like, what about pockle? English doesn't have pockle. Jeepers. Pockle is like a few. It's a distinction that some languages will have, but English doesn't. Also, some languages will have a distinction between singular dual. I think it's usually singular dual pockle or singular plural is sort of the pattern there. Dual being two. The right-hand column of figure 3 shows the results for all layers of the BILMs. Accuracies for the models peak between 52 and 57%, well above the baseline. So this is this very reasonable baseline that they talked about, but below this state of the art, with the transformer overall having the highest accuracy. Interestingly, accuracies only drop 2 to 3% compared to 12 to 14% on the baseline if we remove the assumption of number agreement and simply consider all nouns, highlighting that BILMs are to a large extent capturing number agreement across co-referent clusters. Interesting. So they manually said that we only want to look at things that agree in number, which is something that a rule that they also added in this baseline. And the baseline relies on this very heavily, and their method relies on it much less heavily. And they're taking this as evidence that their method has information on number to some extent. Finally, accuracies are highest at layers near the top of each model, showing that upper layer representations are better at capturing longer range co-referential relationships than lower layers. Let's look at figure 3. Figure 3. Oh wow, it's a small one, huh? Okay. part of speech tagging, constituency parsing, unsupervised coreference. Ow. Interesting. Okay, so various methods of probing the information stored in context vectors of deep BILMs. Each panel shows results for all layers from a single BILM, with the first layer of contextual representations at the bottom and the last layer at the top. So we're sort of looking, here would be the input and here would be the output. So we're moving through the neural network this way. From top to bottom, the figures show the result from the 4-layer LSTM, the transformer, and the gated CNN models. From left to right, the figure shows linear part of speech tagging accuracy, section 5.3, linear constituency parsing, section 5.1, and unsupervised pronominal coreference accuracy, section 5.1. Okay, so we just read about the unsupervised pronominal coreference. So that's which noun is this pronoun referring to. Interesting. So the pattern that I'm seeing here across all of these is that part of speech tagging is more accurate lower down in the model. So we have sort of like a, as you go up, it gets worse. Constituency parsing, as we look at layers with more models, we see that it tends to, with the exception of the LSTM with only 4 layers, be higher in the middle. So it looks like the middle layers are capturing more information about constituency parsing, which is sort of looking at words that are sort of close to your specific word. So I would say that that's local. And then long distance relationships like unsupervised coreference resolution, so this is the one that we just talked about, you can see tend to be better the higher in the model you get with, it looks like there's some noise, but the general pattern is that lower level, mid-level, upper level. So as you go up in the model, you get longer range. The farther you go up in the model, the better you're able to capture long range information. Constituency parsing is best sort of in the middle layers of the model, again with the exception of the LSTM, which only has 4 layers. And then part of speech tagging is better lower down in the model, and part of speech tagging happens at the word level. So I would say that that's like, you know, very, very low level sort of grammatical information. I don't know that I would call it morphological, because I did talk about morphology, and I haven't really seen much discussion of morphology yet. Hopefully we're going to get the morphology. Interesting. Okay, and now I'm assuming we're going to talk about the constituency parsing and part of speech tagging, because we just finished with the unsupervised coreference. Oh, come on, voice. Just a little bit longer. Blah, blah, blah. 5.2. Context, independent, word representation. The word analogy task introduced in Mikolov et al. 2013 is commonly used as intrinsic evaluation of a word vector. Commonly used as intrinsic evaluations of word vector. Tasks, maybe? Something is wrong with the pluralization here. Subject number agreement. Here, we use them to compare the word embedding layer from BILMs to word vectors. The task has 2 types of analogies. Syntactic, with examples such as bird, birds. So bird is to birds as goat is to goats. And semantic, with examples such as Athens is to Greece as Oslo is to Norway. So here we have singular, plural, bird, birds, goat, goats, and capital country. This used to be something on the SAT, but they have removed it. The SAT is a standardized college entrance exam, very popular in the US. Traditional word vectors scored highly on both sections. So the idea is that it sort of, there's information that a word and its plural are similar in some sense, and that a country and its capital are going to be, in the vector space of meaning, will be related close to each other. However, as shown in Table 3, the word embedding layers x sub k from the bilems is markedly different with syntactic accuracies. It's markedly different, with syntactic accuracies on par or better than glove, but with very low semantic accuracies. Oh, so this is where we're going to talk about the morphology. To further highlight this distinction, we also computed a purely orthographically based word vector by hashing all character 1, 2, and 3 grams. So 1, 2, and 3 characters. So we would expect a character-based approach to be really good at capturing morphology, because at least in English you tend to change very few characters in a word. You generally add some to make a morphological difference. Excuse me. Nope, not gonna cough. But we wouldn't expect that, a country and its capital are going to be, very closely related at the character level. Is Panama City the capital of Panama? I feel like that's one of those gotchas. I don't know. I'm sure there's a country whose capital is very similar to the name of the country, but I can't think of one. Vatican and Vatican City, in as far as the Vatican is a country, and it has a capital. I don't know. It's a small country. Excuse me. Okay. In a word with sparse three-dimensional vector, as expected, vectors from this method had near zero accuracy on the semantic portion, but scored well on the syntactic portion, showing that most of these analogies can be answered with morphology alone. As a result, we conclude that the word representation layer in deep ILMs is only faithfully encoding morphology with little semantics. Interesting. I would like to see how well this does on a language like, wow. I may have to wrap up soon. I'm losing it. The voice is going. I would like to see how this would work on a language like Turkish or Hebrew or a Semitic or language or a yeah, I'm pretty sure Arabic has templatic morphology as well. So languages where morphologically related words have fewer overlapping letters when written with Latin script. Because in that case, you wouldn't expect, well, I guess you wouldn't necessarily you're not necessarily going to be training a Hebrew language model on Latin, Hebrew written in Latin script. Oh, Tremendo says, yes, the capital, Panama City. Thank you. So I guess that's one example where low edit distance would actually be a good way of telling if it's the capital or not. But I'm trying to think of a language where morphology isn't necessarily going to be very straightforward to get from a character edit distance. I wish I knew more about the Turkish writing system. Yeah, so I would like to see this done cross-linguistically, because English has very impoverished morphology. We don't have an especially large set of morphemes or grammatical information that we can encode using morphemes. So, okay, I think that's about what I've got today. I'm sorry, guys. Like I said, I'm not quite all the way better, and can definitely tell my voice is going. I don't know if you can. So we will pick back up next Wednesday, hopefully. It may be at a slightly different time. I'm actually going to be in California for Kaggle Days. So if any of you are going to be at Kaggle Days, I will see you there. Hopefully some of you are going to be able to go. We got a lot of good stuff planned for you. I'm going to be so busy. I'm going to be real gosh darn busy that whole week. But I do want to make sure that we get the reading group again, because I do want to continue working on this paper. So far, I've really enjoyed it. I think it's really well written. I think it's good work. And I'm looking forward to reading the rest of it. But that's what I've got today, guys. I'm sorry. I need to go take a nap, I guess, because that's what my life is like right now. I hate being sick so much. I hate it so much. I will talk to you guys on Friday, though. We will be doing some live coding. I'm thinking that I will actually, I've been getting a lot of requests for something to do more machine learning project in R. And I was going to do a workshop this week, but I was too sick to travel, unfortunately. So I've prepared some material, and I might just sort of like give the workshop, but as live coding instead. And then, not next week, but the week after, we won't be having the reading group because I'm going to be live streaming for CareerCon. I'm going to be doing an event on building APIs. So if you're interested in building APIs, we're going to deploy them. It's going to be sort of like a toy example because we won't be doing any authentication, but I think it'll be a lot of fun and hopefully very helpful and a nice practical way, like, hey, I have a model. What do I do now? You can build an API for it. So if you haven't signed up for CareerCons, you can join me on those. Please do. I mean, I'm not going to kick you out, but you won't get the emails with the notebooks if you're not signed up for CareerCon, which would be a great event anyway. So I will see you guys on Friday. I hope you guys have a great week and stay healthy. Don't get sick like I did. Don't travel and go to college campuses, because that'll get you. All right. Goodbye, everybody. Thanks for joining me. Thanks for sticking with me through my horrible hacking and coughing. And I will see you later this week. Bye.